In this presentation of calculus for engineers, we're going to look at inverse Laplace transforms. Now, what we're going to do is determine the inverse Laplace transform of the following expression. G of s, the given function of s, is s plus 1 divided by s squared plus 2s plus 5. Usually what we do in the first instance is to factorize the denominator, the expression I've just indicated with arrows. But the thing is, there's no obvious solution to that. We can express it, the solution with integers. There's no obvious solution there. So what we're going to do is try a different approach. And the approach we're going to use is based on the shifting theorem. So I'm just going to catch up to the next slide. So again, no obvious solution there is evident. So catching up to the next slide, let's try a different approach using the shifting theorems. Consider the denominator. Okay, so s squared plus 2s plus 5, we can break it up into two component parts. S squared, this part here, s squared plus 2s plus 1, and then also 4. Okay. Now, so we can actually re-express the s squared plus 2s plus 1. That is just equal to s plus 1 squared. Now, why did I just pick that s plus 1 squared? That was a sort of informed decision, actually, based on the fact that the numerator is s plus 1. Okay, so if the numerator was s plus 2 or s plus 3, I would respond accordingly. So anyway, down here at the bottom again, we have a denominator. We have it as expressed as s plus 1 all to be squared and then plus 4. So moving on, that's what we have right now. Now g of s is in the form f of s minus a with a equal to minus 1. So essentially what we have here is a function of s plus 1 equal to this. Okay, so this expression over here is a function of s plus 1. Now I use f there because it's connected with the formula sheet. So what we're going to do is, if you look at table entry 15 on the formula sheet, this is what we're going to use here. So the inverse Laplace transform that we're looking for is in this form here. E to the power of at times f of t. This is the inverse Laplace transform of f of s. Okay, specifically f of t is. Okay, so first off what we have to do is find f of s. So we have f of s plus 1, and that's equal to s plus 1 divided by s plus 1 to be squared plus 4. Essentially where we have s plus 1, we just replace it with s. So f of s is simply s over s squared plus 4. Okay, so we have f of s. Now, moving on, we can express f of s, which we just found to be s divided by s squared plus 4. We can actually express that as 2 squared. Now, I'm just going to draw your attention to table entry 11, which is the cosine, related to the cosine. This is s over s squared plus a squared. Okay, so what is f of t, the inverse Laplace transform of that? Well, it is simply cos of 2t. Okay, this s, that's a squared there, so the inverse Laplace transform of this term here, let's bring it, is simply cos of at. So simply a is equal to 2. That's the only thing we're doing there. So f of t is equal to cos of 2t. So we're pretty much done now. So recall that f of t is cos 2t and a is equal to minus 1. The answer we have there so is e to the minus t times cos of 2t. That is the inverse Laplace transform of g of s, which we're going to call g of t, small g of t. And the answer is e to the minus t times cos 2t. There we go. Job done. Presentation over. Thank you very much.